Welcome to next lesson in magnetic fields in matter. In this class, we will discuss some more problems from the chapter magnetic fields in matter. A sphere of radius r carries a charge capital Q, which is distributed uniformly over the surface of the sphere with the surface charge density sigma equals Q by 4 pi r square. This shell of charge is rotating about an axis of the sphere with the angular velocity omega. Find its magnetic moment. The hint is divide the sphere into narrow bands of rotating charge. Find current to which each band is equivalent and its dipole moment, and integrate over all bands. So given the surface charge density sigma is equal to Q by 4 pi r square, we consider a sphere with the radius r, and on the surface of the sphere we consider a narrow band which is shown by this shaded region. So this band has a radius of this much. We can see that if capital R is the radius of the sphere, that is from center to the surface of the sphere, and theta is the angle made by that radius vector from the z-axis, we see that this distance will be r cos theta and this distance will be r sin theta. So r sin theta is the radius of our small narrow band. So this narrow band has a radius of r sin theta, and the thickness of the narrow band is, this is the thickness of this narrow band. This distance is r and this small angle is d theta. This angle subtended by the thickness of the band and the center of the sphere is d theta. Therefore, the width of the band will be r d theta. Now considering that narrow band, we get the width of the band is r d theta because arc is equal, angle is equal to arc by radius. So angle d theta is equal to arc, that is width by radius is r. Therefore, width is equal to r d theta. And radius of the band, radius of this small band is r sin theta. Now the disk is rotating with an angular velocity omega, say about the z-axis. We have to find the magnetic dipole moment. So first we will find the magnetic dipole moment of this narrow band, and then we will integrate the expression for all bands starting from theta equal to 0 to theta equal to pi. First, to find the magnetic dipole moment, we have to find the current through that band into area. Current into area of that band is gives the magnetic dipole moment of that band. So we have to find the current. For that, first we calculate the charge on the band. Charge will be equal to surface charge density into area. That is sigma into area of the band will be equal to circumference into width. That is 2 pi r. R becomes r sin theta here. So 2 pi r sin theta into width is r d theta. So r d theta. The current on the band will be equal to this charge divided by time. So that is equal to, the charge is sigma 2 pi r sin theta into r d theta. Therefore r into r square. So 2 pi r square sigma sin theta d theta divided by time. So time taken by this band to rotate once is equal to period of the sphere. Period of rotation of the sphere is capital T, and that period will be equal to 2 pi by omega if omega is the angular velocity of rotation. Therefore we see that the current on the band is 2 pi r square sigma sin theta d theta by 2 pi by omega. That is equal to omega comes into the numerator, 2 pi and 2 pi gets cancelled, omega r square sigma sin theta d theta. So this is the current on the band. Therefore, dipole moment of the small narrow band will be equal to current into area. That is omega r square sigma sin theta d theta into area of that loop. It is pi r square. It becomes pi into r sin theta whole square, because this is r sin theta. That is equal to pi into omega into r square is r raised to 4 sigma. Then sin theta into sin square theta is sin cube theta d theta. So this is the dipole moment of the small narrow band. Therefore, the total magnetic dipole moment of the entire sphere is obtained by integrating this expression for all narrow bands, starting from the angle theta equal to 0 to the angle theta equal to pi. If we integrate from theta equal to 0 to theta equal to pi, we will cover all the entire surface of the sphere. Therefore, we get the total magnetic dipole moment is equal to pi omega r raised to 4 sigma. Their constants can be taken out. Then integral theta from 0 to pi sin cube theta d theta. That is equal to pi omega r raised to 4 sigma. Now this quantity, the integral can be evaluated by using the steps shown here. The integral is 0 to pi sin cube theta d theta, that is 0 to pi sin square theta into sin theta d theta, that is sin square theta is 1 minus cos square theta into sin theta d theta. Now put cos theta equal to u, we get I equal to 0 to pi 1 minus u square into sin theta d theta becomes minus du. So it becomes minus of integral of du is u minus integral of u square is minus e cube by 3. So put the value of u, cos theta minus cos square theta by 3. Now providing the upper limit, cos pi minus 1 minus cos 0 minus 1 minus 1 by 3 into cos cube theta, cos cube pi is minus 1 minus cos cube 0 is minus 1. So it becomes minus 1 into minus 1 minus 1 minus 2 plus minus 1 by 3 into minus 2 is plus 2 by 3. So it becomes minus 4 by 3 into minus, it becomes plus 4 by 3. So that integral value is 4 by 3. We get the dipole moment M is equal to 4 pi sigma omega r raised to 4 by 3. Now the surface charge density sigma is 4 pi sigma is equal to q by r square. Putting this value of sigma, we get the magnetic dipole moment of this sphere, of the spherical shell rotating with an angular velocity omega about an axis is m is equal to q omega r square by 3. Or in terms of vector notation, we can write it as q omega r square by 3 into z cap if the rotation is about the z axis of the sphere. So this is the answer. Another question is a similar question. If we consider a disk of radius r carrying a charge q such that it is uniformly distributed over the surface of the disk with the charge density sigma equal to q by pi r square. This disk is rotating about its axis of symmetry through the center with angular velocity omega. Find the magnetic moment. So the steps are as in the above problem. You can do the problem by yourself, and the answer will be q omega r square by 4 into z cap. Another similar problem is a sphere of radius r carries a charge q which is distributed uniformly over the volume of the sphere with volume charge density rho is equal to 3q by 4 pi r cube. Now this sphere is rotating about an axis of the sphere with an angular velocity omega. Find the magnetic dipole moment. This problem is also similar to the first problem. The only difference is here the charge is distributed uniformly throughout the sphere. So we have to consider the volume charge density. So you can do it yourself, and the answer will be q omega r square by 5 into z cap. So thank you for watching this video.